Okay, in 3.1.2, system of linear equations. So I just repeat a little bit on system of linear equation. System of linear equation. Okay, we have a representation of system of linear equation as a11 x1, where a11 is the coefficient for variable x1, plus a12 x2 plus until a1n xn equal to b1. So this is how we write in a standard form system of linear equation. Okay, a21 is the coefficient for the second line of linear equation. X1 plus a22 x2 plus plus a2n xn equal b2. Okay, if we have m row of linear equation, you can write as am1 x1 plus am2 x2 plus until am and xn equal to bm. Okay, if this is the right side value, okay, b1, b2, b3 until bm is called right side value or constant. If b1, b2 until bm is all 0, if it is set 0, then this system is called homogeneous system. Okay, otherwise, or if b1, b2, b3 not all 0, not necessarily all 0, okay, or not necessarily each is not 0, but if they are all not 0, okay, any of it can be 0, but only not all 0. Not every b1, b2, b3 is 0. Some of them can be 0, but all cannot be 0. So if all are not 0, so we call the system is called non-homogeneous system. Okay. All right. Okay. So if we were to represent this system of linear equation into a metric representation, we can write as a11 x1 plus in a matrix form, should be in a matrix form, a12 x2 until a1n xn. Okay, so if we were to represent the system of equation into a matrix representation, so we can write in the form of ax equal to b, which is the a is represented by the matrix coefficient, which is a11, a12 until a1n. Okay, a21, a22 until a2n, and the last row is am1, am2 until amn. And x, here is matrix A, matrix coefficient matrix, and variable matrix is given by x1, x2 until xm, until xn. Okay. Okay. And then this is matrix representation for variable x, and the right side value, which is b, is given by b1, b2 until bm. Okay. Okay, example. Let's say we have 2, 4 minus 2, 3, 5 minus 5, 0 to 1. This is in the form of matrix representation equal to 2, 1, 2. Okay, so in linear equation form, in the system of linear equation, we can write as if 2 times x here is 2x plus 4y minus 2z equal to 3x plus 5y minus 5z equal 1, and 0 times x plus 2y plus z equal 2. Okay, next in 3.2 is elementary row operation. Or in the short form is said as ERO. ERO is an operation where we transform the given matrix into the most simplest matrix using this elementary row operation, so that we are able to solve the unknown. We are able to solve this type of equation x, y, z in a much easier way. So this is why we use elementary row operation for matrix coefficient. Okay, so type of operation that involved in elementary row operation is 3 types. Only 3 types is possible. First type is by interchanging 2 rows. We can only interchange 2 rows. Okay, which is row I, you can interchange it with row J. It is possible. Okay, for example, let's say matrix A here. We take this one. Let's say we form matrix coefficient as 2, 4, minus 2, 3, 5, and minus 5, 0 to 1. So if we interchange 2 rows, meaning that we interchange row 1 with row 2. Okay, or we can interchange row 3 with row 2, or interchange row 1 with row 3. Any possible row we can interchange. Let's say if we interchange row 1 and row 2, we can have 3, 5, minus 5, 2, 4, minus 2, and 0 to 1. This is possible. So all the properties of matrix A is equivalent to the properties of matrix that we use the ERO, which is for this case we interchange row 1 and row 2. Okay, this is the first approach for in using ERO. Okay, by interchanging the 2 rows. Okay, next possible procedure for ERO is by multiply all entries in a row by a non-zero constant. Multiply all entries in a row by a non-zero constant. Okay, let's say earlier our coefficient matrix given is 2, 4, minus 2, 3, 5, minus 5. And then 0 to 1. Okay, so now if we were to perform operation number 2 by multiply all entries in a row by a non-zero constant. So let's say row 1 we multiply by 2, for example. Okay, row 1 we multiply. Each operation must only be performed at one time only. Okay, not possible we multiply row 1 by 2 and then multiply row 2 by 4. That is not possible. It should be one approach or one operation at one time. Okay, so here we have 4, 8, minus 4, 3, 5, minus 5, 0, 2, and 1. Okay, so this matrix A is equivalent to this matrix. Okay, for operation number 3, it is replace one row by the sum of itself and a multiple of another row, and a multiple of another row. Replace one row by the sum of itself and a multiple of another row, meaning that, okay, let's say matrix A, we take as 2, 4, minus 2, 3, 5, minus 5, 0, 2, 1. Okay, so now replace one row by the sum of itself and a multiple of another row, meaning that, let's say row 1 as, we replace row 1 by the sum of itself and a multiple of another row, plus 2 row 2. So row 1 become row 1 plus 2 times row 2. So it become 2 times, so 2 plus 2 row 2 means 2 plus 6 is 8. Here 5 times 2, 10, 10 plus 4 is 14. Here minus 10 plus minus 2 is minus 12. Okay, 6, 8, 4, 10, 14. Here minus 10, minus 2 is minus 12. Okay, and the rest remain the same. Okay, so this matrix equivalent to this matrix, and their properties are all the same. So this is examples of how we do elementary row operation. We can also perform on other row, not necessarily the first row. We can perform it on the first row, on the second row, and also on the third row, as long as we follow the procedures set by operation in 1, 2, or 3. Okay, next is row echelon form. Or in a simple form, it is write RE, row echelon form. We are going to differentiate between row echelon form and reduced row echelon form. Okay, first let's have a look at the row echelon form. So there are properties for row echelon form matrix. So the properties must meet this criteria, which is for row echelon form matrix. First, all 0 entries must be at the bottom. Entries must be at the bottom of the matrix. Okay, second property is for each non-zero entry, each non-zero entry is called leading entry. Each non-zero, the first non-zero entry is called leading entry. Okay, but for this, for convenience, it is changed to 0. Okay, for convenience, but not necessarily it is changed to 1. Okay, for convenience, it is changed to. Later I will show you how to change the leading entry to 1. It is changed to 1. Okay, but not necessarily it must be changed to 1. Okay, but only for convenience it is changed to 1. Leading entry meaning that all entries that is not 0. Okay. Okay, so we will do operation to get this leading entry using ERO. Okay, the third properties is each leading entry, the one we have here, the first non-zero entry, each leading entry is to the right of all leading entry. In the rows above. Okay, so the first each leading entry for row 1, row 2 must be to the right of all leading entry in the rows above. Okay, so meaning that, okay, as an example, we have matrix like 0 to 5, 1 to 3, and 0, 0, 4. Okay, so this is not in the form of row echelon because the first non-zero is here. So the first non-zero meaning that it is not to the right of all leading entry. So we must change the first leading entry here, which is non-zero, make this row as first row. So meaning that we have to interchange row 1 and row 2. So it becomes 1 to 3 and 0 to 5 and 0, 0, 4 like this. So the first non-zero is 1, and actually it's not necessarily 1, but for this case, this is by accident it is 1. Okay, but not necessarily it should be 1. Okay, so the first entry is on the left. Okay, and all the 0 should be on the right. So all the it is like a triangle. Okay, it is like a triangle here. So we must set all 0 should be on the right side. So it become a triangle like this. So this is called a row echelon form. Okay, it's called row echelon form. All 0 entries must be at the bottom. Okay, all 0 entry must be at the bottom, but not necessarily all 0. Okay, but the row which has more zeros must be at the bottom. Okay, each non-zero leading entry, is changed to 1. This is for convenience. Okay, each non-zero is called leading entry. Okay, each non-zero is called leading entry. For convenience, it is changed to 1. For this one, this is the leading entry. Okay, since leading entry here, and this one is 0, so we must change. We must put the leading entry first. Okay, next, each leading entry is to the right of all leading entry in the rows above. So each leading entry must be to the right. Each leading entry is to the right of all leading entry in the row above. Okay, so each leading entry must be to the right. So all the rows below should be at the bottom. So this is how we get the row echelon form. Okay. Okay, for this is row echelon form. For reduced row echelon, okay, for reduced row echelon form, which is RRE, for row echelon form, it is not unique. So everybody able to get a different matrix for row echelon form because it is not unique. As long as it follows the procedure set in each criteria here, it is called row echelon form. Okay, for reduced row echelon form, the condition. Okay, the leading entry must set to 1. must set to must be 1. So we need to change it into 1 given any constant that we obtain, and with another condition, each column that contain leading entry, each column that contain the leading entry has 0 everywhere. Okay, any column yang ada leading entry 1 tu, entry yang lain-lain tu adalah 0. Macam tu. Okay, dan RRE form is unique. So, tadi RE form is not unique, but now the reduced row echelon form of a matrix must be a unique form. Adalah unique. Macam tu. Earlier we have the RE form. RE form is matrix given by matrix 1, 2, 3, 0, 2, 5 and 0, 0, 4. Okay, so now this is the RE form. If we were to transform this into RRE form, RRE form must be in the form of 1, 0, 0. Yang leading entry 1 tu elsewhere is 0. 0, 1, 0 and 0, 0, 1. Macam tu. This is the RRE form. Okay, to transform from RE to RRE form, then we need to perform ERO, elementary row operation. So how do we perform this? Okay, now look at this properly. How do we transform this? First, send this, since this is 1, then fine. Okay, if the first entry is not 1, then we need to change into 1 first. Okay, since this is 1, then fine. And the rest, okay, 0, fine. Okay, next set this to 1. Okay, to set this to 1, meaning that row 2 need to divide by 2. Okay, so this 1, 2, 3. Row 2 divide by 3 is 2 divide by 2 is 1, 5 divide by 2. And the rest follow like this. Okay, next this one 0, fine. Okay, and the rest of the element in the same row of leading entry must be 0. Next is perform this, make this 0. So how to make this 0? By use the third operation, which is row 1 minus 2 times row 2. Okay, so row 1 minus 2 times row 2, so that we have this 0. Okay, so this one is 1, 2 minus 2 times this is 0. Okay, 3 minus 2 times this, 2 times 5 over 2 is 5. So 3 minus 5 is minus 2. And the rest is the same. Okay, this is done. Okay, this is in RE form. This is in RE form. So next is this one. Okay, the leading entry for this one must be this. This one must be set to 1. Okay, this one must be set to 1 because this is the leading entry on the right side of leading entry of the previous row. Okay, so row 3 must be divided by 4. Okay, so we have 1, 0 minus 2, 0, 1, 5 over 2. Check this first, okay. 0, 0, this one divided by 4 is 1. Okay, so since this is 1, we can make this 0 and make this one 0. Okay, so to make row 1 here 0, row 1 is row 1 plus, do the operation on the leading entry that we have changed to 1. It is much easier to make that operation. Row 1 plus 2 times row 3. 1, 0. So row 1 here plus here is 0. And row 2, this one can be performed simultaneously. Okay, this one, to make this and this 0, we can perform simultaneously. So row 2 is minus 5 over 2 row 3. So this is 0, this is 1, and here 5 over 2 minus 5 over 2 makes 0. Okay, and here is 0, 0, 1. Done. So this is the elementary ERO operation that we need to perform in order to reduce matrix from row echelon into reduced row echelon form. Okay.